Okay. Hello, everyone, and welcome to another reaction to another. Oh god. What is this? What am I having to endure today? Well, it seems like the idea of how black holes form has certain categories and ideas and then collapses when you get certain sizes.
So I can buy this slow.
Shit.
Move forward. This front black hole mergers defying our understanding of physics? What's up with that? Well, nobody doesn't love black holes, or at least doesn't love talking about them. Avoid them if you see one coming. Back in my day in graduate school, many moons ago, we know how to make black holes as the endpoint of stellar evolution. How does that work? Well, the sun, after another 5 billion years, has been around for 5 billion. So after a 10 billion year lifespan, it's going to run out of fuel in its core. And then it will release its outer layers of gas into space and lay bare a dense core that we call a white dwarf. And create a very beautiful nebula in space, by the way. We'd be in the middle of it, we'll be long dead by then, but it would be a very beautiful nebula to other star systems if they trained a telescope on us. That's one way a star can die, with the mass of the sun. But how about stars that are 8 or 10 times as massive as the sun? Well, they have a very different fate, because much more is going on in the core of those stars than is going on in the core of our sun.
Right.
Above a certain mass, the endpoint of a star is not just gently release the outer gases. The endpoint of that star is it runs out of fuel, its core collapses, and undergoes total spontaneous nuclear fusion, blowing the guts of the star to smithereens. It can outshine the entire galaxy in which that explosion takes place. We call these explosions supernovae. Typically, at the end of a supernova, what's in the core of that is a dense ball of neutrons. In keeping with astronomical naming and nomenclature, we call that a neutron star. Very dense, much denser than the white dwarf left over from when the sun dies. What happens if the star is 10, 11, 12, 15 times the mass of the...
What's an electron star? And is it possible? And under what conditions is an electron star possible? Why am I mentioning this? No one talks about electron stars as even potential because... Oh wait, that's just a black hole.
sun? Well, it has so much mass that when the core collapses,
That was a
it
joke.
keeps collapsing. The collapse, in a way, is stronger than the explosion that would otherwise take place. It collapses in on itself, bada bing. Thus is born a black hole. That star would have lost some of its mass along the way, but what got folded into the black hole? 6, 7, 8, 9, 10 times the mass of the sun. We call those stellar mass black holes. And we expect them to be dotting the galaxy where stars had been born, laid out their lives, and died. Okay. Towards the end of my time in graduate school, there were suspicions that the centers of galaxies...
I mean, you got... How big is the biggest stars we've ever seen? And it's not stellar mass, it's huge. So
these might harbor a black hole. Not just any black hole, a supermassive black hole. Way more massive than the one you'd get from the endpoint of stellar evolution. So we started looking. This predates the Hubble telescope now. Get the best ground-based telescopes, the best spaceborne telescopes. In some galaxies, we find a supermassive black hole. And in keeping with astronomical extrapolations, many of us said, me included, if we have a supermassive black hole in these 3 galaxies, and these are the first 3 galaxies we've even looked for them, then clearly every galaxy has a supermassive black hole. Why not presume that and then go...
Well, the presumption is that a cluster of stars the size of a galaxy can only be held together by something as big as a supermassive black hole, unless it's like some massive, beyond massive star that somehow is bigger than some black holes, but not too big that it explodes.
Check. And that's what we did. Bring in the Hubble telescope, which had very good vision down into the centers of galaxies. Sure enough, every galaxy we have ever observed in its center has a supermassive black hole. Even we have a supermassive black hole. The one in the center of the Milky Way is 4 or 5 million times the mass of the sun. How about Andromeda? Andromeda's
Okay.
almost our twin. It's another
Let me explain something to you. Right? If you go by cube and whatever, certain objects that are a number of size, because of how cubes work, well, spheres aren't cubes, but there's some generalization that can be actually done about that. Cubing a sphere is not impossible, but in a general sense, you can. There's a relationship there. That's not the point. The point is that if you have, let's say, 1,000 by 1,000 by 1,000, right? So it's a billion. Well, that's just 1,000 times wider, right? But it's a billion times more massive. Something.
And Spiral Galaxy, and it's the closest big galaxy to the Milky Way.
A similar
So it's a
relationship
little bigger than
happens
us,
with
but
spheres.
does it have a supermassive black hole? It sure does. And what's its mass? 100 million times the mass of the sun. We don't know how to make them yet, but clearly this is a thing in the universe.
Superhydration keeps me 24/7 moisture.
I like this commercial, but we're moving on.
All right. So that sent people to the drawing board. Well, the center of the galaxy is quite a busy place. There are gas clouds that'll lose energy that can dip down into the center, get eaten by these black holes. These black holes can also attract stars and flay them as they come too close. There are mechanisms for these black holes in the centers of galaxies to grow by dining upon material that wanders too close. So we started modeling that, and we're now feel comfortable with supermassive black holes in the centers of galaxies. We even learned that the more massive the galaxy is, the more massive the black hole is. That kind of makes intuitive sense. You still want to be able to explain it. The itty-bitty galaxies, they have little itty-bitty black holes. Itty-bitty supermassive black holes. Okay, that gives us 2 categories of black holes. Stellar mass black holes and supermassive black holes that you'd find in the centers of galaxies. And that was a peaceful...
You know, we have, like, how the stuff keeps on getting bigger and bigger, proper scale comparisons of things. Like, Hertzkazak did a great video on that. But, like, the world's biggest stuff versus the world's smallest stuff, I think, was one of the videos where he did that comparison, and I might look at that in this video to be like, this is an example of big stuff. And stellar massive, certain size black holes versus the fact that you can just imagine a collection of gas of whatever size, depending on how it coalesces, will just make whatever size star you want. Right? And depending on the size of the explosion, you end up with solar systems. And like, if it's interesting to think of the size of the object that originated this solar system, right? It turned into a nebula, the nebula collapsed, turned into the different stuff that we are now. And we, meaning the entirety of all the asteroid belt, and every planet, the sun itself, and you realize, like, our planet, our moon, and you realize that, like, the size of objects it makes sense that they would just vary. It could become any amount because of initial conditions. It could just be whatever size that it ended up being. We've seen stars that are like Ooey Scooey or whatever is the one that comes off the top of my head. It might not even be the biggest. I don't know. I don't remember which one is the biggest. I don't really care. But the point is, they get big. And orders of magnitude bigger. And the galaxy that we have, there's a star out there that existed or still exists that our entire galaxy fits inside, which is cool. And so you think that type of an object, so big, like, obviously, if you look into billions of light years away, you can see the earlier and earlier and earlier times of the universe. You should be able to see potentially the biggest type of stuff. And if you're not seeing the biggest stuff, you're not seeing the real earliest past that there is. And obviously the light hasn't been able to get to us yet. It's the assumption that skewed red light, because of how it goes through the supposed bending of space-time and the entire distance that is traveled, infrared light would have obviously the amount of light that we assume had to have faded into infrared over the distance. So it had, in order to get to us, it actually did travel that extra distance, which equals an even deeper past. But here's the question: why would you start with infrared? There are much bigger wavelengths than infrared. And why not make a sensor, just go all out and go with the maximum sensor that you can make? Right? Because clearly you should be able to make the sensors be at whatever frequencies necessary, from infrared all the way down to the lowest waves of frequencies that you can detect. And then, obviously the microwave background has something to say about that. So, like, there has to be, like, every frequency variant leading up to, in between all those points. And even beyond microwave. Whatever.
Distance for decades. All right? There was no other reason to think we'd have black holes of any other size. And then they started showing up. Intermediate mass black holes. Black holes that can't be the end of stellar evolution. We know stellar evolution. That's the triumph of 20th century astrophysics. Decades studying the birth, life, and death of stars. We got that. You're not going to get a 20 or 30 mass black hole that comes out of a star that has died. All right? And we got the supermassive black holes.
I don't think you really believe that. We're gonna have to repeat that for just the audacity that was in that statement. No way.
Holes. Stellar mass black holes and supermassive. I think we'd have death of stars. Got the supermassive black holes. Suppose you find a black hole that's 30, 40, 50, 100 times the mass of the sun. We have no idea how you make them. So, let's return to the drawing board. The drawing board is an active thing.
Wait,
that comes out of 20th century astrophysics. Immediate mass black holes. Black holes that can't be the end of stellar evolution. We know stellar evolution. That's the triumph of 20th century astrophysics. Decades studying the birth, life, and death of stars. We got that. You're not going to get a 20 or 30 mass black hole that comes out of a star that has died. All right? And we got the supermassive black holes. Suppose you find a black hole that's 30, 40, 50, 100 times.
Why? Do the math. What kind of explosion? I mean, you didn't mention hypernova. First of all, shame on you. Because supernova and hypernova are two vastly different categories of explosion. So you're leaving out bits of information that I already know of, which begs me to think that there are other simple things that you're overlooking, like the size of the absolute biggest stars that could have been in the beginning. We don't know. There's no reason to assume just how big they could have been. And what if their mass forced them to immediately collapse into a black hole? Well, that's how we get supermassive black holes. Right? The ones the size of galaxies and all that. Clearly. But there's no reason why, like, once you get to a certain size, right? You don't need to go through, and here's the thing. He mentions about the star turning into this other thing, and then into the neutron star, and then into the. This is not the age. This is not how. This isn't the process every star goes under. Right? You don't just say that it starts with star. Like, what if you turn into a red giant star? What happens then? And then you last for extreme number of millions and billions of years longer than regular stars, which burn slower. What if you had stars that are of types that literally, because of the collapse, it's not because they run out of fuel. It's because of there's something about mass, there's something about critical density, there's something about what it's really capable of doing inside of itself. There's videos about a black hole star being just a concept, where you have a black hole that's inside of a star. The core has collapsed, but the star is so massive that it literally can't just evaporate. It has to take a long time before that black hole will actually eat out the rest. So there's no like center core of iron. There's a core of a black hole, which is huge. And theories of that are lost in this video.
The mass of the sun. We have no idea how you make them. So, let's return to the drawing board. The drawing board is an active thing that's always up in the office.
Did you say how you make the supermassive black holes in the first place? We just assume that you have the galaxy. What if we aren't even a first series galaxy? That blows your mind. Because that means that something else exploded to make the galaxy. And then those different puffs coalesced in different ways to make the bundles of stars that are around the galaxy and their solar systems, which are further amounts of collapse. Literally, whatever size that you start with, that's your building block. We already know that our star is a part of a multiple... We aren't even the third generation star. Like, it's fourth or more. Is what it might be third. The point is, stuff exploded multiple times to make the stuff that we ended up having on our planet. That's how it works. Right? A normal explosion of a star, you get, like the formation of a star, you get the iron and you get up to that point, and then you have an explosion, and then you need certain other explosions to have the formations of other stars. You have to realize, at some point, this galaxy might be what was originally a nebula, an explosion of an original star. Right? This entire galaxy, not just the black hole, obviously, but the entire galaxy. That's how it's formed, basically. It's not just that you have a big clump and it did a thing. Like the black holes inside of, and the way they are formed is like the way stars are formed, and they explode like this, but then they leave behind a black hole, and then you have whatever size of them based off of the total mass of the original star. And there's no reason to believe that there couldn't be just any random size initial state collection of gas. There's no reason to think that that isn't the case. Because the other thing is, there's this interesting phenomenon about us in our galaxy being part of a great attractor, and then the great attractor isn't even the size of the biggest stuff that there is in the universe. Like collections of galaxies, and then you got even bigger things. Like, come on. the biggest black holes or the biggest whatever else. I saw a video and I referred to the Great Attractor, and I was like, the Great Attractor is tiny compared to bigger structures in the universe, which blew my mind because I thought that was it's a cluster of galaxies all being pulled by an eddy current towards what they assume is a great attractor. It's just a flow of electromagnetism all towards. It's like if you pull on the bed sheet, it's literally what's happening. An object moves through that space. The electromagnetic field in the area pulls and flows like the bed sheet, and the electromagnetic field is the stuff between electrons, or I refer to the stuff between electrons and protons, the connection they're in. That's everywhere. It's not just stuff that is connecting protons and neutrons, it's everywhere. So that flow is the eddy currents. The Great Attractor is easily explained. And it doesn't have to be a massive, strong magnetic thing. It just has to be something that was powerful, big, strong enough, moved through that area of space, and then the eddy currents just keep going along with that initial setup of the flow. So it's possible to explain that area where we're going to is like way earlier. There was a star. It went and did one of those things where all of the stuff just jets out in one direction like a pulsar. Only it was so big. And that entire jet stream is what makes the Great Attractor eddy current. Just a theory.
Okay? Is there a way to make an intermediate mass black hole? That is still unresolved. Could it be that you make binary black holes that are 10 solar masses each or 8, and then they merge, and the two masses combine, and then they find another black hole mysteriously somehow, and they merge? Is this the product of mergers? Or is there its own process that can come together and make these from scratch? We just don't know. We got top people working on it. Top black hole people.
So it's the understanding that certain size categories of stars make certain size categories of black holes, and these other black holes fall into a size category that can't be described by the natural way that we understand most things exploding, becoming a black hole eventually. But again, the initial star formation, right? You gotta imagine, we start off with just nothing but a gigantic cubic meter of gas. Million light years of gas, right? All directions, a big giant cube of gas, and it can coalesce into whatever size of big puffball and stellar mass that you can imagine. But not just that, what if there's even a billion light year collection of gas that happens to just coalesce into the entire whatever size, which is impossible. That's the size of the entire universe coalescing into one thing. That's too big. That's not possible, right? Well, just anywhere in between a regular sized star and the biggest star we've ever seen And then you gotta imagine how big the stars actually could have been. And there's all sorts of stars in between those layers, and we're just mentioning some of them. But it's the idea that they come in these certain distinct size categories, that they don't come in between category sizes. And I feel like that's like kind of silly. Like, why would they not just come in any random variety of size? And the answer is, of course, the way that they form in the first place, the way that that formation, that amount of gas and materials interacts, and the way that collection develops.
Good thing. I can't wait to find out what the best model is for creating these black holes that had no previous way to understand how they came into existence. Aliens did it.
I mean, there's obviously, if you can make a bigger black hole, the Hawking radiation theory of it shrinking down really does not work at all, because assuming it has to take quadrillions of years for a black hole to evaporate, there's no way that's the way that we have a black hole that is of this size just because it was bigger and then it shrunk. Even that is not enough to explain it. But that's not a method he's mentioning. That it can just shrink down into this. Well, we haven't had enough time to have that happen. Just hand wave that and mention that, please.
An active area of research. A headline might say we have to new physics. Okay, maybe. To describe it as though that's a problem? No, it's an exciting time. That's what being on the frontier of science is all about. Being stumped. Let's gather at our conferences, let's write our research papers, let's do the peer review thing, let's figure out what's going on and move forward this frontier of modern astrophysics.
Oreos are very big black holes with a bunch of gooey centers that are spun so fast that they turn into discs, and then we eat them with milk ways. Whatever, I don't care. I don't hate the video. Look, it happened a day ago. What are you? Okay. One guy got very confused. Okay, I like that. I have never seen Raf with Math. We're gonna look at that, probably. But well, okay, we'll cue that up. We'll cue that up. But let's go look at largest star in the universe. And there you go. So that's like
one of the largest stars ever discovered has a radius 1,700 times our sun. If you put it in our solar...
So why can't you get a black hole from that? It doesn't look like the correct scale. Just saying.
It would reach past Jupiter.
That is definitely not to scale. What the fuck?
Orbit. On the other end of the spectrum, one of the smallest stars we've ever discovered is only about the size of Saturn. Just barely big enough to be a star. About twice as big as our sun is this blue-white star, Sirius. Its bluish-white color means that its surface is 2 to 5 times hotter than our sun. A big step up is Arcturus. This red giant is 25 times as large as our sun. Its expanded size and deep red color tells us that it's much older and about 2,000 degrees cooler than ours. Next is the red supergiant that we started with. And speculated to be
Looks
even
good.
larger is this red hypergiant,
Right.
Stephenson 218. We think it's over 2,000 times the size of our sun and growing. As a star dies, it begins to bloat due to the changing chemistry inside it. So this star is dying. If you learned something, subscribe.
Okay, so the thing that I'm stuck on is how big is that bitch? You just said a comparison to another star. You didn't say how many light years across that is. Light minutes. Light hours? Light farts. Anyway, yeah, that's not helpful. Here's a video that's helpful. Perhaps.
What is the largest star in the universe?
Why the
And
fuck
why is
did
it
you
that
do that?
large? And what are stars anyway? Things that would like to be stars. We begin our journey with Earth, not to learn anything, just to get a vague sense of scale. The smallest things that have some star-like properties are large gas giants or sub-brown dwarfs, like Jupiter, the most massive planet in the solar system. 11 times larger and 317 times more massive than Earth, and more or less made of the same stuff as our sun, just much, much less of it. The transition towards stars begins with brown dwarfs, failed stars that are a huge disappointment to their mums. They have between 13 and 90 times the mass of Jupiter. So even if we took 90 Jupiters and threw them at each other, although fun to watch, it wouldn't be enough to create a star. Interestingly, adding lots of...
What? No, okay, here's the problem, okay? You're talking about putting a bunch of Jupiters together. Jupiters are puffy. It's a puffball. So why don't you take something that's more dense and shove it into Jupiter? Huh?
mass to a brown dwarf doesn't make it much bigger, just its insides denser. This increases the pressure in the core enough to make certain nuclear fusion reactions happen slowly and the object glow a little. So
I want to skip forward, actually. Where is the comparison to the biggest thing?
Wondering what foods are safe for braces?
Shut up.
There's no
That guy, Galactic, this big thing. They mentioned the same star, obviously, because it's the one that people are talking about. There's not one bigger yet. And here's the thing. Composition matters. So you get things that are big, but you get stuff that is full of a bunch of different stuff. And ones that have turned into red giants, as far as I understand, are like bloated stars. It's like a Jupiter, where it's got a core, but its outer edge is a lot of puff. And you end up wondering about the bigger stars. They have an inner core, but the outer side could be just a lot of puff. So again, what if you have a larger, more dense, but also dense thing?
Want to play a bit more with size stuff? We have good largest stars in the universe, hypergiants. Hypergiants are the giant phase of the most massive stars in the universe. They have an enormous surface area that can radiate an insane amount of light. Being so large, they're basically blowing themselves apart, as gravity at the surface is too weak to hold on to the hot mass which is lifted away in powerful stellar winds. Pistol Star is 25 solar masses, but 300 times the radius of the Sun, a blue hypergiant aptly named for its energetic blue starlight. It's hard to say exactly how long Pistol Star will live, but probably just a few million years. Even larger than the blue hypergiants are the yellow hypergiants. The most well-studied is Rho Cassiopeia, a star so bright it can be seen with the naked eye, although it's thousands of light years from Earth. At 40 solar masses, this star is around
North
500 times the radius of the Sun and 500,000 times brighter. If the Earth were as close to Rho Cassiopeia as it is to the Sun, it'd be inside it, and you would be very dead. Yellow hypergiants are very
funny. Well, it is.
rare, though. Only 15 are known. This means they're likely just a short-lived intermediate state, as a star grows or shrinks between other phases of hypergiantness. With red hypergiants, we reach the largest stars known to us, probably the largest stars even possible. So, who's the winner of this insane contest? Well, the truth is, we don't know. Red hypergiants are extremely bright and far away, which means that even tiny uncertainties in our measurement...
Hold on, why are they bright? They're red. Red means not as much light as other stars.
...can give us a huge margin of error for their size. Worse still, red hypergiants are solar system-sized behemoths that are blowing themselves apart, which makes them harder to measure. As we do more science and...
Okay, so Okay. So the biggest things we have seen, red hypergiants, compared to a solar system. You have no idea about this universe, do you? I'm talking everyone. Again, the model of how material is made, you have a hypernova and everything. Certain solar ends with massive explosions create the materials such as uranium. You can't get everything beyond iron without explosions. So, yeah. Like you have to go extremely big to do this. Again, you gotta realize, if there are stars the size of entire solar systems, which obviously our solar system is the result of an exploded star. That to me is that's just math in my brain. Is that not how it happened? The original star exploded. But you gotta realize, that original star exploded. It already had crazy stuff inside of it that normally stars don't have. Because, again, it's not just one, like, the star formation and the material formation formats, the way it happens. And the reason I say we have to be at least the third generation of star or more is because of the different types of materials that are made and the different ways that those extreme levels of materials are able to be made only happen with like the initial explosion of a star versus also the hyper explosion of a star. Meaning that definitely happened in our past. But another explosion happened also that made more of the more regular stuff in betweens. So you have to just excuse the thought that if you can have something the size of a solar system, but it, like, you gotta realize, try turning the clock back a bit, realize how big of a star you'd have to have so that it, 1, hypernova, 2, collapsed probably made a solar system, then exploded again, made what is left over in our, as we know it, solar system, which is probably why we have two different belts, but no. It's not why we have two different belts of meteorite stuff. Like, you would think, like, just whatever cloud stuff happens, all of the materials that don't end up becoming a planet or a star or Jupiter just end up becoming the belt. But here's the thing, right? That's an interesting theory. What if the outer belt was the remnants of the original explosion star, which then had to collapse, itself then exploded, spreading everything out, but also all of that stuff that could have become the second belt, or the inside belt, then was also formed, as well as all the rest of the planets. And we end up with the star that we know. So we're definitely Series 3 star. Again, at least. Of course, that's not how material decides to coalesce. It could have coalesced in any amount. So, it could be that you have something the size of a solar system, however many times it exploded and then collapsed, doesn't matter, because it could have all collapsed and then exploded again, and we would still end up with, like, you gotta ask yourself, how did our solar system get made? But then you gotta ask yourself, well, why is that not also the similar way that a supermassive black hole galaxy get made, but you have stars bigger than our entire galaxy? But I'm not hearing about that. Or is it not the biggest star? It's the biggest black hole. Hold on. Turn this word into black hole, please. Largest black hole in the universe is a completely different thing, and there we go. They also did that, which is surprisingly not the same video.
The size of black holes is insane. The smallest
Did you
known
curse
black hole
Kazakh?
is J1650. Its diameter is about as long as Manhattan, but it's got a mass of 3.8 of our suns. Step up is this black hole, Messier 15. It's about the size of Mars, with a mass of 4,000 suns. Now we're getting to the lower limit of what's considered a supermassive black hole. This one's about the same size as our sun, but 100,000 times its mass. And get this, the black hole at the center of our galaxy, Sagittarius A, is about this size compared to our sun, and has 4 million times its mass. We captured this image of it in 2022. Now comes the truly insane. The black hole in galaxy M87 weighs 5.4 billion suns. It was the first to be imaged in 2019. And finally, one of the largest black holes ever discovered weighs a whopping 66 billion times more than our sun. We're making a...
Okay, so... Just that synopsis alone... Again, this is all taken from textbook, basically. If you have something the size of 66 billion of something, you gotta wonder. Also, it's the size of the black hole. The black hole is not necessarily a galaxy forming thing, but galaxy is definitely black hole. But again, I'm left wanting, because Huh.
Longer video about black holes, so subscribe. The size.
Go to the middle again. Shut up. Go to the middle.
And get this, the black hole at the center of our galaxy, Sagittarius A, is about this size compared to our sun and has 4 million times its mass. We captured
I'm sorry, what size?
this image of it in 2022. Now comes the truly insane. The black hole in galaxy M87 weighs 5.4 billion suns. It was the first to be imaged in 2019. And finally, one of the largest black holes ever discovered weighs a whopping 66 billion times.
Okay. So again, how do they form?
Life moves fast.
Why the hell did I make
Send
those
money
videos in
quickly
that format? I don't
with
know.
Download the app today.
Whether you hold it in
Okay, shut up.
Black holes. In contrast to things like planets or stars, they have no physical size limit and can literally grow endlessly. Although in reality, specific things need to happen to create different kinds of black holes, from really tiny ones to the largest single things in the universe. So how do black holes grow? And how large is the largest of them all?
You don't have to do... To be clear, the supermassive black hole inside of our galaxy didn't get its way by eating. It could have, but it didn't.
This video will not discuss how black holes work or how they form, since we've looked at that in detail in our black hole and neutron star series. You can check them out afterwards. For now, we're interested in finding the largest thing in the universe. Let's start really, really small. Primordial black holes. The smallest kind of black holes may or may not exist. If they do, they're probably the oldest objects in the universe, older even than atoms. They would have formed just after the Big Bang, when the universe was so dense with violent energy that any tiny pocket that was just slightly more dense than its neighbors could produce a black hole. The smallest primordial black hole that could still be around would be 8 trillion kilograms or so, the mass of a big mountain. And yet they would be no bigger than a proton.
Yeah.
A primordial black hole with the mass of Earth would barely be larger than a coin. This makes them very hard to find, so we haven't actually observed any yet. If
So it's not electrons?
they exist, they may even be the mysterious dark matter that holds galaxies together.
Oh, you mean the electromagnetic field that is holding electrons to protons. And yeah, that's everywhere. And that is dark matter. But never mind.
Let's move on to the kinds of black holes that we know for sure are out there. Stellar black holes. To make a black hole, we need to compress enough matter so that it collapses into itself. After that, the more mass we throw at it, the larger it becomes. In today's universe, only the most violent cosmic events can create the necessary conditions, such as the merger of neutron stars or when the core of a very massive star collapses in a supernova. To have a unit to work with here,
Right,
we'll use
with
the
two
mass of our
methods.
Sun, about 2 million trillion kilograms. The smallest known black hole has 2.7 times the mass of the Sun, which works out as a sphere around 16 kilometers in diameter, large enough to cover Paris.
You found that?
Another lightweight black hole is the companion to the V723 Mon red giant star. This star is 24 times larger than our Sun, 30 million kilometers in diameter. And yet, it's thrown around by a tiny black hole just 17.2 kilometers wide. This tiny...
Okay. Interestingly enough, shared... Okay, interestingly enough, our sun is being pulled around and technically circles an area that is defined by its relationship with everything else in the solar system, including Jupiter. Most importantly, Jupiter. Well, most contributed Jupiter. So the thing is, that area that that is orbiting is like what was the word for Lagrange point? It's like that, but in the relationship of the Sun and Jupiter, instead of a Lagrange point of... No, that's not the right term. It can't be. Or is it? The combined forces of the planet and the planet Earth, there's like an equal distant area that is like, you can orbit steadily here. Something like that. But that's not what is making the Sun and Jupiter have a mutual... I guess I think of it as the sum of the two tugs. In which case... move on.
Thing bullying the star is so much smaller that we can barely even show them in comparison. One of the largest known stellar black holes is M33X7. It currently spends its time eating a 70 solar mass blue giant bit by bit. As all that stolen matter circles towards the black hole, like water going down a drain, friction heats it up to temperatures high enough to shine 500,000 times brighter than our sun. And yet, X7 is only 15.65 solar masses and 92 kilometers wide, just big enough to cast a shadow on Corsica. To grow much larger, black holes have to either devour a lot of stars, or better, merge with one another. The instruments that make it possible to detect these mergers are very new, so we're currently discovering a lot of exciting things. Like two massive black holes that we detected in a galaxy 17 billion light-years away. As they spun around each other violently, they released more energy in the form of gravitational waves than the combined light from all the stars in the Milky Way in 4004.
You said billions of light years away? Meaning that explosion happens billions of years in the past? We're only feeling that now. Imagine an explosion that lasts for billions of years. Or its effect still reaches billions of years later. Yikes.
100 years. The new black hole they formed is about the size of Germany and is 142 solar masses. And here we hit a curious gap in scale. There are lots of black holes up to 150 solar masses, and then there's nothing for a long time. Until we suddenly hit black holes that are millions of times more massive. Which is a bit confusing because we had this idea that black holes are consistently growing and growing. But for the most massive black holes, this process is not fast enough to explain their existence today.
Okay. Eating and growing versus a star collapsing. It's like you're trying to create them from in a backwards way. 'Cause to me, I would start with the formation of the biggest things and not concern myself with how small ones are made. nearly as much.
The universe is simply not old enough for these supermassive black holes to have formed by eating stars and merging with each other. Something else must have happened.
Yeah.
To explain how we got the largest black holes in the universe, we might need the largest stars that ever existed, quasi-stars. To get a sense of scale, we can compare them to the largest stars that exist today. Our sun is like a grain of sand next to them.
This is where we
don't know
theorize
if
about
quasi-stars
even
actually
bigger
existed,
stars.
but they're an interesting concept when it comes to supercharging black hole development. The idea is that the matter in the early universe was so dense that quasi-stars could grow to thousands of times the mass of our sun. The cores of these stars might have been crushed by their own weight so much to actually collapse into black holes while the star was still forming.
Yep.
In contrast to stars today that would destroy themselves in the process, inside quasi-stars, a deadly balance could emerge. Gravity pressed the supermassive star together, feeding the black hole and heating the material falling in to such a degree that the radiation pressure kept the star stable. And so these quickly growing black holes might have been able to consume the quasi-star for millions of years and grow far bigger than any modern stellar black hole.
A tasty and nutritious snack.
But here's the thing. Here's the rub about that. You still end up with galaxies. So, again, you start with the collection, and because of the extra big size, and for whatever reason, it doesn't matter how much mass stays in the area after the explosion, because sometimes you can end up with mass that is ejected and doesn't stick around. So it's possible to then make results that are, again, random and be whatever other size that you can end up making. You have to realize that it doesn't matter how dense the original the beginning universe was. It matters about how do I put it? Every time you get let's say that you start trying to move a bunch of stuff from all edges, right? You gotta realize that from one side it can only reach so far, and then everything starts to kind of tug away. But you also realize that we talk a lot about antimatter. Give me a second.
1,000 times the mass of the Sun and wider than the entire Earth. These black holes might have become the seeds for supermassive black holes. So now we arrive at the kings of our universe, the largest single bodies.
Hold on. Just shut up for a second. You just said quasi-stars. Not even the size not even ones that are making a black hole the size of our own supermassive black hole. You're not thinking big enough. Again, the amount of pull of all the matter that you can possibly collect into a thing, and then it starts doing fusion and whatever else, you're going to have the outer reaches of everything not be able to form in the same way. And so they'll end up making whatever stuff. You gotta realize, galaxies have a spin to them. That's a crazy amount of spin. And that happened because of all of the in the motion and all of that. Huh.
In existence. The centers of most galaxies contain a supermassive black hole, and they are monstrous. In the Milky Way, we have Sagittarius A star, a supermassive black hole with about 4 million solar mass.
And of course, our stars aren't that big. Our star is not that big in comparison to other stars in the solar system. Apparently, our supermassive black hole in our galaxy is not even close to being big compared to some other things that are out there.
That is calm and collected and just does its thing. We know it sits there because we can see a number of stars being thrown around by a seemingly empty spot. And despite its incredible mass, it's...
Again, the seemingly empty spot that is where we orbit the star and Jupiter is because of their collective influence on each other, not a supermassive black hole. So you're making assumptions about you must have a black hole there. No, there could just be a collection of all their masses, and because of their motion through space, that's why there is that area that they seem to orbit. It's because of their influence all on each other. Unless they don't stick around long enough to be able to continue to influence each other. In other words, why would other stars also be interacting with this space? Then you might have a black hole.
Radius is still only...
For example, there is not a black hole in the center beside our star. That's not how that works. So you got to be careful about what you think about why things are gravitationally connected. Because, like, those edge case bits of information like that can help you get away from certain, like, generalizations and biases.
17 times our sun. Smaller than most giant stars, but millions of times more massive.
Yeah.
Because supermassive black holes are so massive and located at the center of galaxies, many people imagine them as being a bit like the sun in the solar system. An anchor that glues everything else together and forces it into an orbit. But this is a misconception.
Nah.
While the sun makes up 99.86% of all the mass in the solar system, supermassive black holes usually only have 0.001% of the mass of their galaxy. The billions of stars in galaxies are not gravitationally bound to them. Instead, it's the gravitational effect of dark matter which holds them together. Many supermassive black holes aren't gentle giants, especially when they're feeding on the clouds of mass in their galaxy.
So you're literally understanding that there is this substance throughout the entire galaxies that moves along with them, like spinning the bedsheet or any other fluid dynamics thing that you want to think of. When it comes to literally any size matter that's big enough to tug around other things, you gotta realize the smallest stuff is gonna be moving along with that as well. So we're not orbiting, or we're not held together by the black hole, which is, again, why the stuff on the edges is able to be moving as fast as it does and still hold in with everything else in the galaxy. Because the stuff on the edges, according to everything else, should fling off, but doesn't because of other mass effect.
The one at the center of the BL Lacerti galaxy is devouring so much material that it produces jets of plasma accelerated to nearly the speed of light. If Earth were orbiting this huge body, it would seem 115 times larger than our sun in the sky, and we'd be burned to a crisp in seconds by its glowing hot accretion disk. At this point, black holes become so large that stars seem ridiculously tiny compared to them. The galaxy Cygnus A has a supermassive black hole with 2.5 billion solar masses and 14.7 billion kilometers wide, which would mean that if it took the place of our sun, it would swallow all the planets and stretch halfway to the edge of our solar system.
Yeah.
It's devouring so much mass and material that it churns its disk into a kind of magnetic funnel, spewing gas out, making tremendous radio lobes towering over the galaxy 500,000 light years in diameter. That's 2.5 Milky Ways wide.
You know, an electron does the same thing, only in just one direction. But the electromagnetic field is also, like, it bubbles out and it creates the same kind of shape. It makes sense why any electromagnetic field flows in that way. So it makes sense that when you have something big, it follows the same format.
Another pretty large supermassive black hole sits in the galaxy Messier 87. It has 6.5 billion solar masses and was the first black hole we got an actual photo.
When you see those big towers that are leading out, the amount of EM field that is flowing in a toroid around that area of that influence is that big. Imagine solar winds and sunspots and all of that stuff. But instead of that, it's like the electromagnetic field is so excited and so huge and so big that it's like, well, it could be that, or it could just be that when it shoots out further and further and further, like any good mushroom cloud, eventually it stops. Some of the stuff stops, and the rest of the stuff hits what slows down, so it billows up, making mushroom cloud type stuff. That's just another fluid dynamic thing. You don't need an EM field to achieve that.
Or rather, of the glowing gas around the edge of a menacing shadow. This sphere of darkness is so large that it covers our entire solar system. And yet, there is a scale even above these kinds of objects. Ultramassive black holes.
Yep.
We reach the most massive black holes, perhaps the largest single bodies that will ever exist. These black holes have eaten so much that they've grown to tens of billions of solar masses, their gravity the engine for a quasar, an accretion disk shining brighter than thousands of galaxies full of stars. So massive that they deserve a title of their own: ultramassive black holes. The ultramassive black hole at the center of galaxy OJ287 is 18 billion solar masses. It's so big that it has a supermassive black hole nearly 40 times larger than Sagittarius A star orbiting it. This thing defies imagination and is really hard to compare to anything.
You just simulated it, so it's imaginable.
It can comfortably fit 3 solar systems side by side inside of it.
Yeah.
Let's end this insane competition and get to the King of Kings. Ton 618, a black hole that we can observe consuming galaxies worth of matter, is shining with the brightness of 100 trillion stars, visible from 18 billion light years away. It has an incredible 66 billion solar masses, a black hole so large that it would take light a week to reach the singularity after crossing the event horizon.
Didn't I hear about the star with 66 billion solar masses? Is it 66 million? Large numbers, and not hearing them close to each other in a big chart makes it hard to pay attention.
About but 11 solar systems could sit inside of it side by side.
See, I
It may
like
very
that.
well be-
I like that comparison. Although light years is kind of a better measurement.
The largest single
it's
body in
actually
the
a
universe, but in reality, it's probably even larger. Since Ton 618 is so far away, we only see what it looked like 10 billion years ago.
Yeah.
In any case, black holes are scary and mysterious. And
Here's the thing, right? You're saying you're seeing this massive thing, and it's a black hole, and it's super far away, which means it's super in the past, meaning even before that, something had to have been collective to make it.
and gigantic. They'll be here after everything else dies and growing larger and larger.
As
Okay,
long as there's
now
stuff
let's
around.
do the trip again. From the smallest possible black hole all the way up to the largest.
Just absolute. Yeah.
The Shoppers Beauty Plus event is
Just absolutely dwarfing everything else around it. I bet you that music was inspired by the pulsing of a pulsar as it rotates, because the signal of the beam is like constantly oscillating, because it's also like that. It's not just spinning, but it's like its spin is spinning. That makes any sense? Anyway, so in my brain, they talked about a star that's capable of making a black hole that is only the size of what we experience, and it's only a star forming a black hole that is only the size of smaller than our supermassive black hole. There's a gigantic gap between like that and the largest black holes, and then we just say, nah, we're not going to assume anything about anything anymore, because it's so big that God knows it probably doesn't make a lot of sense to try to make sense out of it. Kilometers. That video sucks. Sorry. It was made, but it's like, can I scroll through this? I didn't know you could do this. That's crazy.
Is there an end to it? Is there one?
Yeah. Give me back my controls. I didn't even know you could navigate YouTube like this.
Black hole jets like this have been seen all around the universe, including in our own cosmic neighborhood. Push much of the loose gas out beyond the boundaries of the new galaxy.
This black hole is eating so fast it breaks the laws of physics.
This reinforced how important black holes are to our understanding of the early universe, which was in and of itself a problem because the black holes themselves broke our models too. To further complicate the matter, we're not completely sure that supermassive black holes are the grown-up version of stellar black holes in the first place. Although it's...
No, because black holes, okay, they can get bigger, but generally in order to make them in the first place, you have to have a cataclysm event. And then the size could go up and usually goes down, depending on what's around them. I don't know. Well, we're good. I like that. That's fun.
A little over 10 years of experience in the commercial nuclear power industry. Only 14, 15 billion years old, so you're looking beyond the horizon of essentially how far we can see using light. That's fascinating, man.
Than the combined
Did you say,
light from
wait,
all the stars in the Milky Way.
did you just say millions and we are looking beyond what we can see? We already can see 13 billion light years away. What are you talking about?
4,000.
What the hell are you talking? Wait.
The new black hole they formed is about the size of Germany and is 142 solar masses. And here,
I know I'm in landscape mode. Shut up.
we hit a curious gap in scale. There are lots of black holes up to 150 solar masses, and then there's nothing for a long time, until we suddenly hit black holes that are millions of times more massive, which is a bit confusing because we had this idea that black holes are consistently growing and growing. But for the most massive black holes, this process is not fast enough to...
Why would they be growing and growing? They can only eat the stuff that's around them. Instead, assume that you had something bigger, cataclysm, and then you end up with a black hole of that size.
explain their existence today. The universe is simply not old enough for these supermassive black holes to have formed by eating stars and merging with each other. Something else must have happened. To explain how we got the largest black holes in the universe, we might need the largest stars that ever existed. Quasi-stars. To get a sense of scale, we can compare them to the largest stars that exist today. Our sun is like a grain of sand next to them. We don't know if quasi-stars actually existed, but they're an interesting concept when it comes to supercharging black hole development. The idea is that the measure...
This is that same video that they did later on.
Way to add a little fun to your day.
Fuck. Does everyone have, like, no ads?
Black hole stars or quasi-stars. Okay.
The early universe was so dense that quasi-stars could grow to thousands of times the mass of our sun. The cause of these stars might have been...
I don't want to hear thousands of times the mass of our sun when I hear about stars that are 66 solar masses or something. I'm sorry. You can't... What? I'm going back.
science and our instruments improve, whatever the largest giants. The most well-studied is Rho Cassiopeia, a star so bright it can be seen with the naked eye, although it's thousands of light years from Earth. At 40 solar masses, this star is around 500 times the Pia, a star so bright it can be seen with the naked eye, although it's thousands of light years from Earth. At 40 solar masses, this...
Okay. So we got 40 solar masses there, and then we end up with...
This gas will then go on to form another generation of stars of...
Yep, like how
evolves, it will probably shed even more mass and shrink down. The star that is currently thought to be among the largest we've found is Stephenson 218. It was probably born as a main sequence star a few tens of times the mass of the Sun and has likely lost about half its mass by now. While typical red hypergiants are 1,500 times the size of the Sun, the largest rough estimate places Stephenson 218 at 2,150.
Okay.
Solar radii and shining with almost 500,000 times the rough estimate places Stephenson 218 at 2,150 solar radii.
2150. Okay, so them versus the black holes, and it's the same video we just saw, so we could have just watched that.
Unleash your inner lion
I love
as
this
the
for me.
Weighed so much to actually collapse into black holes while the star was still forming.
Yep.
In contrast to stars today that would destroy themselves in the process, inside quasi-stars, a deadly balance could emerge. Gravity pressed the...
See, my imagine is the idea of a quasi-star, the stuff that can make the supermassive black holes, is on the lower end of what you should be imagining, and I would assume any black hole you have already witnessed is also the result of a mass engulfment event where everything just gets pulled in, and it doesn't matter how long it stays in star format, it turns into a black hole pretty soon after, because all the stuff that was around it fused and turned into pretty much immediately a black hole that also absorbed the nearby area, possibly.
Supermassive star together, feeding the black hole and heating the material falling in to such a degree that the radiation pressure kept the star stable. And so these quickly growing black holes might have been able to consume the quasi-star for millions of years.
You gotta realize, a black hole is nothing but a digestive system. It can only eat things so fast, depending on its size, based off its radius. So, if you have a smaller one, you can only reach everything that is in your radius. And so, well, I mean, you could reach everything within your radius, but you could also, but you can't, like, actually have it pull in and transform any more than it already is. There's a rate at which, depending on the spin or something, like a slower moving black hole could have a bigger amount of suction because it's not flinging everything away from itself? ?
And grow far bigger than any modern stellar black hole. Black holes several thousand times the mass of the Sun and wider than the entire Earth. These black holes might have become the seeds for supermassive black holes. So now...
So, again, you're assuming a relatively what is supposed to be the biggest, beyond any bigger, the biggest star that we've ever seen. And because we can look so far back, we've seen a lot of variety option of history of star, but not main sequence stars. We've never seen those. That's too far in the past. It's beyond what we can actually like visually see, possibly. And it's more likely that, like, you gotta realize, stuff that is so big, but then the density of it throughout everything else, and there are others, there are so many calculations you can do to figure out the total density of what the universe was in the beginning stages of everything, or whatever, however it started.
We arrive at the kings of our universe, the largest single bodies in existence. The centers of most galaxies contain a supermassive black hole, and they are...
Did it say how you get from several thousand to millions, though?
Yeah.
Monstrous. In the Milky Way, we have Sagittarius A star, a supermassive black hole with about 4 million solar masses that is calm and collected and just does its thing. We know it sits there because we can see a number of stars being thrown around by a seemingly empty spot. And despite its incredible mass, its radius is still only 17 times our Sun. Smaller than most giant stars, but millions of times more massive.
Yeah.
Because supermassive black holes are so massive and located at the center of galaxies, many people imagine them as being a bit like the Sun in the solar system. An anchor that glues everything else together and forces it into an orbit. But this is a misconception. While the Sun makes up 99.86% of all the mass in the solar system, supermassive black holes usually only have 0.001% of the mass of their galaxy. The billions of stars in galaxies are not gravitationally bound to them. Instead, it's the
It's interesting to think the size of the galaxy is bigger than the thing that it's orbiting. But the thing that it's orbiting is still in the center. And the amount of stuff that it would have to get in order to get that big had to have been as big, you know, the entire galaxy, and then that collapsed into the black hole. Like, you gotta wonder how it actually formed.
Yeah, it's true, because there's on the order of billions to trillions of stars, so it would have to be like trillions of solar masses.
Effect of dark matter which holds them together. Many supermassive black holes aren't...
See, he said what I was saying. Trillions. Not nowhere near what we've already either witnessed or quasi-stars, which are like, okay, bigger than the biggest star we've ever seen, but still not trillions of solar masses.
Giants, especially when they're feeding on the clouds of mass in their galaxy. The one at the center of the BL Lacerti galaxy is devouring so much material that it produces jets of plasma accelerated to nearly the speed of light. If Earth were orbiting this huge body, it would seem 150
POV, you're about to die.
times larger than our Sun in the sky, and we'd be burned to a crisp in seconds by its glowing hot accretion disk. At this point, black holes...
I always love the name black holes because the accretion disks, like it said, are many, many times brighter than the Sun. So the term black hole, I guess if it didn't have anything to absorb, it would be truly black, and then you wouldn't be able to see it.
Yeah.
So large that stars seem ridiculously tiny compared to them. The galaxy Cygnus A has a supermassive black hole with 2.5 billion solar masses and 14.7 billion kilometers wide, which would mean that if it took the place of our Sun, it would swallow all the planets and stretch halfway to the edge of our solar system. It's devouring so much mass and material that it churns its disk into a kind of magnetic field.
You gotta wonder, again, and it's not just about the size of the thing that originated and then made our solar system. Because you have to also think about all the other stuff that's in the galaxy as well. And it's like, it's just whatever way that the nebula decided to coalesce. Which is nutty.
Spewing gas out, making tremendous radio lobes towering over the galaxy 500,000 light years in diameter.
So again, like any fluid dynamics, the moment stuff at these points, like here and there, the stuff that is being shot out finally decides that it's not able to keep its speed, and it does keep on going, but a lot of it starts to slow down, billow out, fluid dynamics does its thing, and you end up with these lovely clouds like that. Yeah.
That is fascinating.
Yeah.
That is fascinating. Huh.
That's 2.5 Milky Ways wide. Another pretty large supermassive
Our
black
entire
hole
galaxy
sits in
times
the
two.
galaxy Messier 87. It has 6.5 billion solar masses and was the first black hole we got an actual photo of, or rather, of the glowing gas around the edge of a menacing shadow. This sphere of darkness is so large.
Here's the thing, right? What if the accretion disk versus our perspective is either straight on, flat, straight on, or flat, and anywhere in between, where the only reason we're seeing it is its rotation is in some way oriented not to be like directly in line with our perspective. So what if you had like our line of sight? So if you have something that's out there and its accretion disk is like extremely straight compared to our perspective, it would be just like a thin wafer or something.
That it covers our entire solar system. And yet, there is a scale even above these kinds of objects. Ultramassive black holes.
I've never heard ultramassive. That is a cool name and a cool font, though.
Now we reach the most massive black holes, perhaps the largest single bodies that will ever exist. These black holes have eaten so much that they've grown to tens of billions of solar masses, their gravity the engine for a quasar, an accretion disk shining brighter than thousands of galaxies full of stars. So massive that they deserve a title of their own. Ultramassive black holes. The ultramassive black hole at the center of galaxy
Yeah, I've heard of quasars, but not ultramassive.
287 is 18 billion solar masses. It's so big that it has a supermassive black hole nearly 40 times larger than Sagittarius A star orbiting it. This thing defies imagination and is really hard to compare to anything. It can comfortably fit 3 solar systems side by side inside of it. Let's end this insane competition and get to the King of Kings. Ton 680, a black hole that we can observe consuming...
Appropriately named. A ton.
galaxy's worth of matter is shining with the brightness of 100 trillion stars, visible from 18 billion light years away. It has an incredible 66 billion solar masses. A black hole so large that it would take light a week to reach the singularity after crossing the event horizon. About 11 solar systems could sit inside of it, side by side.
A light week. Huh. Wait. Oh yeah, our solar system, the sun is only light minutes away from us. Never mind.
It may very well be the largest single body in the universe, but in reality, it's probably even larger. Since Ton 618 is so far away, we only see what it looked like 10 billion years ago.
So, if we see something 10 billion years ago, and it's already... It looks like a stellar nursery, to be honest. It doesn't look like a proper black hole. It looks like... But here's the thing, right? Whatever basic thing happened and the black hole was formed, and then the rest of the stuff is still gas that it's sucking up, means that there was a lot. You gotta imagine if it's a disk that's around it. I mean, the first format is that everything seems to form into disks, right? So that's one way that they coalesce and collect and become more dense. Because they used to be so much wider and bigger and everything, but then you end up crush that because of the spin, or flatten it out because of the spin, and you end up with... Obviously I'm going to like his video, but if I can find the button.
Black holes are scary and mysterious and gigantic. They'll be here after everything else dies and growing larger and larger. Okay, now let's do the trip again. From the smallest possible black hole
until they start shrinking. I don't know, I can't add any more things to it. The fact that we're talking about something that is was it billions or millions of solar masses, and then you end up with, or standard the size of our sun masses, and then you end up with stars that only get up to like what was it, 40 or 66 solar masses or something? Like, it puts a good scale on it. I love the idea of how big it is compared to a solar system, but again, the imagination of the properties that formed it, and then it's ironic, you have your own videos, right, of how they formed, but I'd have to look those up.
Wondering what foods are...
And I'm not in the mood to scroll through your stuff. But the next video I'll probably watch is amphetamines, so I won't have to worry about it. I have a pin from their store. Toodles! I don't know how to really give you anything concrete